Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on zeros, singularities and poles. Lecture number 9, in which I will give you tips to detect the kinds of singularities through limit and limit points. Firstly, I will give you the simple knowledge about a function, its principal part, and how to simply detect removal singularity, poles, and essential singularity. Let function of z is expressed in Laurent series as follow. Function of z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n plus sigma n equal to 1 to infinity bn z minus z naught whole to the power minus n. This part is called principal part. Principal part means the terms having negative power of z minus z naught. The singularity of the function depends on the principal part of the function. Number 1, if a number of terms in principal part be finite, then z equal to z naught is a pole. Number 2, if a number of terms in principal part be infinite, then z equal to z naught is essential singularity. Number 3, if after calculation fz contains no principal part, then z equal to z naught is said to be a removable singularity. Now we use limit and limit points. To detect the kinds of singularities. Number 1, limit z tends to z naught function of z equal to finite, then z equal to z naught is a removable singularity. Number 2, limit z tends to z naught function of z equal to infinite, then z equal to z naught is a pole. Number 3, if limit z tends to z naught function of z does not exist, then z equal to z naught is essential singularity. Number 4, if z equal to z naught be the limit points of zeros, then z equal to z naught is isolated essential singularity. Number 5, if z equal to z naught be the limit point of poles, then z equal to z naught is non-isolated essential singularity. Now, with the help of example, we will show that why the singular point is a removable singularity or a pole or isolated singularity or non-isolated singularity. Example 1. Let function of z equal to sin z by z. Here, if z equal to 0, then fz is not defined. Therefore, z equal to 0 is a singular point. Singular point means at that point function is not analytic. Here, function of z equal to 1 by z, we expand sin z, z minus z cube by factorial 3 plus z to the power 5 by factorial 5 minus dot 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 dot, and this equal to 1 minus z square by factorial 3 plus z to the power 4 by factorial 5 minus dot 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 dot. In right side, we do not get any term containing negative power of z. Here we see this is 1 means z to the power 0 here. Here z square z to the power 4. No negative power of z. Therefore, we do not get any term in principal part. So, z equal to 0 is a removable singular point. the limit, use of limit. Limit z tends to 0, function of z equal to limit z tends to 0, sin z by z equal to 1. This is finite. Therefore, z equal to 0 is a removable singular point. If the limiting value is finite, then it is a removable singular point. In shortcut, we may use this. By expansion, here limit z tends to 0, function of z equal to limit z tends to 0, 1 minus z square by factorial 3 plus z to the power 4 by factorial 5 minus dot 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 dot, and this will be 1 if z equal to 0, z equal to 0. This is also finite. Therefore, limit z tends to 0, function of z equal to finite means z equal to z naught is here 0, is a removable singular point. Now example 2, if z equal to cos z by z, here for z equal to 0, function of z is not defined. Therefore, z equal to 0 is a singular point. Not defined means not analytic. Here cos z by z, f z equal to 1 by z, we expand cos z, 1 minus z square by factorial 2 plus z to the power 4 by factorial 4 minus dot 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 dot, and this equal to 1 by z minus z by factorial 2 plus z cube by factorial 4 minus dot dot dot. Here the terms containing negative power of z be only 1 by z. Therefore, number of terms in principal part equal to 1 equal to finite, means finite number of terms in principal part. Therefore, z equal to 0 is a pole. Now we use the limit. Limit z tends to 0, function of z equal to, here we use limit z tends to 0, 1 by z minus z by factorial 2 plus z cube by factorial 4 minus dot dot dot. Here z equal to 0, this is 0, this is 0, but this is infinite. This is equal to infinite. We know that if limiting value of function of z is infinite, then z equal to 0 is a pole. Therefore, z equal to 0 is a pole. This is simple pole. Because in principal part we have 1 by z equal to 1 by z minus 0 to the power 1. This is 1. So z equal to 0 is a simple pole. Now we give example 3. Function of z equal to sine 1 by z. Here, if z equal to 0, then the function is not defined. Implies that function is not analytic. At z equal to 0. Therefore, z equal to 0 is a singular point. Function of z equal to sine 1 by z. If we expand this, equal to 1 by z minus 1 by z cube by factorial 3 plus 1 by z to the power 5 multiply factorial 5 minus dot dot dot. In right side, number of terms containing negative power of z be infinite, because here we see z to the power minus 1, z to the power minus 3, z to the power minus 5 dot 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 so on. Infinite number of terms containing negative power of z. Therefore, number of terms in principal part equal to infinite. So, z equal to 0 is essential singular point. Use of limit. Here limit z tends to 0, function of z equal to limit z tends to 0, 1 by z minus 1 by z cube factorial 3 plus 1 by z to the power 5 factorial 5 minus dot 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 dot. Here this equal to, this is 1 by 0, infinitive minus infinitive plus infinitive and so on. That means, therefore, limit z tends to 0, function of z does not exist. So, z equal to 0 is an essential singular point, because we know that when limiting value of the function does not exist, then it contains essential singular point. Now question is whether it is isolated essential singular point or non-isolated essential singular point. For this we use the limit point, concept of limit point. Here let function of z equal to 0 implies that sine 1 by z equal to 0 implies that 1 by z equal to n pi implies that z equal to 1 by n pi implies that z equal to plus minus 1 by pi plus minus 1 by 2 pi dot 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 dot. Since for each value of z equal to plus minus 1 by pi plus minus 1 by 2 pi comma dot 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 dot, the fz vanishes. Means value, if we put this value here, this will be 0. Therefore these are zeros of function of z. Limit n tends to infinity z equal to limit n tends to infinity 1 by n pi, this equal to 0, and this 0 is essential singular point. This is equal to essential singular point. Therefore limit point of zeros is an essential singular point. Hence z equal to 0 is an isolated essential singular point. We know that if a singular point be the limit point of zeros, then that singular point will be an isolated essential singular point. Example 4. Let function of z equal to 1 by sine 1 by z. Here for z equal to 0, the function is not defined, implies that the function fz is not analytic at z equal to 0. Therefore z equal to 0 is a singular point. Now fz equal to 1 by, now we expand sine 1 by z. This is equal to 1 by z minus 1 by z cube factorial 3 plus 1 by z 5 factorial 5 minus dot 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 dot. We take common 1 by z 1 minus 1 by z square factorial 3 minus 1 by z to the power 4 factorial 5 plus dot 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 dot. And this equal to z, this goes in numerator, and 1 minus 1 by z square factorial 3 minus 1 by z to the power 4 factorial 5 plus dot 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 to the power minus 1. And this will be equal to z 1, here minus, we use binomial theorem, plus 1 by z square by factorial 3 minus 1 by z to the power 4 factorial 5 plus 1 by z square multiply factorial 3 minus 1 by z to the power 4 factorial 5 plus dot 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 dot, here also plus dot 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 dot, this is square plus dot 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 dot. In right side we get an infinite number of terms containing negative power of z. This is z to the power minus 2, this is z to the power minus 4 and so on. Therefore, number of terms in principal part equal to infinite. Therefore, z equal to 0 is essential singular point. If we find a limit, we get limit z tends to 0 if z does not exist. So this also shows that z equal to 0 is an essential singular point. Here 1 by z equal square means 0 square, infinitive minus infinitive plus infinitive and so on. So we do not get any limiting value of this function. So this is an essential singular point. Now question is whether it is isolated essential singular point or non-isolated singular point. Let sin 1 by z equal to phi z. When phi z equal to 0 implies that sin 1 by z equal to 0 implies that 1 by z equal to n pi implies that z equal to 1 by n pi, n equal to plus minus 1 plus minus 2 and so on. These are zeros of phi z, implies that these are poles of 1 by phi z implies that these are poles of function of z. Limit point of these poles equal to limit n tends to infinity 1 by n pi. This is 0. This is equal to essential singularity of fz. We know that limit point of poles be non-isolated singular point. Therefore, z equal to 0 is a non-isolated essential singular point. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.